Welcome to this video on higher order ODEs. By the end of this video, you will be able to solve higher order ODEs. So why higher order ODEs? Well, higher order ODEs appear in many applications, and in a second we'll look at one example. Now, how do we solve these? Well, it turns out that a higher order ODE can be transformed into a system of first order ODEs. So here's one example, Newton's second law describing the fall of a parachuter. So here we got this parachuter, and on the parachuter, if we want to describe the acceleration that the parachuter experiences, we have to use Newton's second law. And onto the parachuter, there's gravitation that acts on him. So d2y dt squared is equal to g, if y is positive in the downward direction. And then, fortunately, there's also a drag force acting on the parachuter because of the parachute. And that acceleration due to the parachute is simply a drag coefficient divided by the mass of the parachuter times the velocity squared. And that is going in the upward direction. Okay, so now we have a constraint, or constraints in this case, that we have to know to be able to solve this higher order ODE. And the constraints are that at time equal to 0, the position of the parachuter shall be y0, and at time equal to 0, the velocity of the parachuter shall be v0. Okay, so this is a second order ODE because it contains the second derivative. Now, we also know that the velocity is the first derivative of the position y. Okay, so dy dt is equal to v. So let me use this in the equation that used Newton's second law. So that means that the second derivative of y with respect to t is really the first derivative of the velocity with respect to time. So that Newton's second law can also be written as dv dt is equal to this right-hand side, g minus ct over m times v squared. And now if we look at this here, suddenly I have a system of two ODEs, but the highest derivative in the system is first derivatives. Right? So I have now a system of first order ODEs. What was the trick? Well, the trick was to replace the first derivative of y with a new variable. And in this case, that was physically motivated, the velocity, v. Okay, here's another example. Rather complicated looking nonlinear higher order ODE. The fourth derivative of y with respect to time minus 2 times the third derivative with respect to time plus the first derivative squared, right? The square makes this nonlinear, minus 10 is equal to 0. And because there's the fourth derivative in here, we need 4 constraints, and those constraints are given here. Y at t equal to 0 is 1. The first derivative with respect to time indicated by this y dot is equal to 2 at t equal to 0. The second derivative is equal to 3 at t equal to 0. And the third derivative is equal to 4 at t equal to 0. Now, the strategy to transform this into a system of first order ODEs is to introduce variables for each of the derivatives of the dependent variable y. And we start with the 0th derivative, and we will end with the n minus first derivative. So let's start. I'm going to introduce a new variable x1 that will be the dependent variable y itself, right, the 0th derivative. I'm going to introduce a second new variable x sub 2. That will be the first derivative. A new variable x3, that will be the second derivative. And finally, a new variable x4, that is the third derivative. Now, the highest derivative in the ODE was the fourth derivative. So here I have to introduce new variables up to the 4 minus 1, up to the third derivative. Okay, so I got these new variables now. And now what I have to do, or realize really, is this, that if I take the derivative of the first variable, I simply get the second variable. So dx1 dt is equal to x2. If I take the derivative of the second variable, then I will simply get the third variable. That's by definition. If I take the derivative of the third variable with respect to time, I simply get the fourth variable. And now finally, if I take the derivative of the fourth variable, I should reach the highest derivative that I have in the ODE, and now I can use the ODE. So dx4 dt is ddt of the third derivative, that's the fourth derivative. And that's the term that appears up here in the ODE itself. So this is then equal to something that I can derive directly from the ODE. Well, I have minus 2 times the third derivative of y, but the third derivative was, well, the third derivative was x4, right? So it's minus 2 times x4 plus the first derivative squared. But the first derivative was my second variable. So I simply have plus x2 squared and then minus 10 equal to 0. Now you'll note that but this particular ODE doesn't contain the second derivative, so there's no x3 that appears in this last ODE equation, but that's not a problem. So now we have a system, right? We have a system of first order ODEs that are subject to constraints. Now let's express the constraints in terms of our new variables, because x1, x2, x3, x4 are now the solution variables of my system of ODEs. So I have a constraint that y at t equal to 0 is 1, but for my new variables, y is equal to x1. So this constraint is simply x1 at t equal to 0 is equal to 1. Next up, dy dt, that's x2. Well, x2 at 0 is supposed to be equal to 2. That's the constraint that was given. Next up, the second derivative was equal to 3, but the second derivative is now called x3. So x3 of 0 is equal to 3. And then finally, the third derivative, which is now called x4, has to be equal to 4 at t equal to 0. So we have now initial constraints for each one of our variables x1, x2, x3, x4 that form the dependent variable of the system of ODEs. And those are now just simple. It's a simple system of first order ODEs. But what if we had a system of higher order ODEs? Right here I've just looked at a single higher order ODE. What if we have multiple higher order ODEs? Well, then each one of them would become a system with these new variables, and we will then have a system of systems of first order ODEs. But it all boils back down to simply first order ODEs that we know how to solve. Now let's do one more example. Let's transform the following higher order ODE into a system of first order ODEs. Okay, so what was the process? The process was introduce new variables, starting with the 0th derivative of the dependent variable. The dependent variable in this case here is h, all the way to the n minus first derivative. Now let's first figure out what is the order here of this higher order ODE. Well, there is here a fourth derivative, so the order here is 4 for this ODE. So now we'll just have to introduce new variables. And let's start with x1 is equal to the actual dependent variable h. x2, next variable, is equal to dh dt. x3 is equal to d2h dt squared. And then x4 is equal to d3h dt cubed. Right, I have a fourth order ODE, so I have to go up to the third derivative introducing new variables. Now let's build the system of ODEs. Right, the first 3 equations are very simple. I just take each one of these new dependent variables and take their time derivative. dx1 dt is equal to Well, if I take the time derivative of h, I get this, right? dh dt. So that's equal to x2. Next up, dx2 dt. If I take the time derivative of dh dt, I get d2h dt squared, and that's equal to x3. So equal to x3. Next up, the time derivative of x3. Let's see what happens. The time derivative of d2h dt squared is d3h dt cubed, which is equal to x4. Okay. And then if I take the derivative of my last variable, dx4 dt, right, I take the derivative of the third derivative of h with respect to t, I will then arrive at the fourth derivative, which is the order of my ODE up here, where I can now then use the ODE itself. Right? I just need to substitute the values in. So I get then dx4 dt, right? Let me mark this. dx4 dt is just this, right? Because x4 was the third derivative, so dx4 dt is the fourth derivative, plus 2 times, there is an h missing here, 2 times the square root of the second derivative. Let's see where the second derivative is. d2, right? That's the second derivative here. Okay, so that would just be 2 times the square root of x3 plus 4 times dh dt. So dh dt here is x2. So plus 4 times x2 plus the sine of h squared. Okay, h squared. H is equal to x1. So I have here the sine of x1 squared is equal to the cosine of t. Right? And if you look at this here now, right, you'll see that we have converted this fourth order ODE into a system of 4 first order ODEs. These very simple 3 first ones here, and then using the original ODEs, substituting in these newly defined variables, we have converted this one here into a first order ODE as well. And then together with the appropriate constraints that are not part of this example problem here, we could solve this fourth order ODE by simply solving these 4 first order ODEs. Thank you for watching.